Hello everyone, welcome to this video session. Today we will see another example using Simscape Toolbox, that is PWM Controlled DC Motor. So it's a model that is developed by MathWorks. To open this model, we need to run a command in our command window. So the command is ee_motor_DC_PWM. So if we just write this in our command window and just click enter, it will directly open the model. So you can see now this is the model. So where uh, DC motor has been controlled using PWM voltage, and that is controlled using a H-bridge. So basically this model shows how to use the controlled PWM voltage and H-bridge block to control a motor. This DC motor block uses manufacturer datasheet parameters, which specify the motor as delivering 10 watt of mechanical power at 2500 RPM and no load speed as 4000 RPM when run from a 12 volt DC supply. Hence, if the PWM reference voltage is set to max value of 5 volt, then the motor should run on 4000 RPM. But if it is set it to 2.5 volt, then it should run approximately at 2000 RPM. So we will run this for these two different voltage value, and we will check and validate the manufacturer dataset if our motor is correctly parameterized or not. This simulation model parameter is set to average for both controlled PWM voltage and H-bridge blocks. So that is resulting in first simulation. We will change it to PWM mode and we will see it. Now, if we just open this, so this is the PWM reference voltage. So now you can see the voltage value is set to 2.5 volt. Then the positive and negative terminal are connected with control PWM reference positive and negative, where the reference PWM frequency is set to 4000 Hz and the simulation mode is set to average. Then the PWM is connected with the H-bridge PWM port and reference is connected with reference reverse and braking, where the negative is sorted with it. Inside H-bridge, if we just go, here you can see the power supply mode has been set to internal. The simulation mode has been set to average, same like this control PWM voltage. Then the regenerative braking always enable. And then after that, when there is some braking and due to braking the power law, that we can regenerate our electrical energy. So this regenerative braking is very useful phenomena for electric vehicle. Then the load characteristics, you can see it is set to smooth. The output voltage magnitude, amplitude, that is the basically the voltage value for the voltage rating for the DC motor is 12 volt. And the total bridge resistance is 0.1 ohm and freewheeling diode to protect this circuit is set to 0.1. This is the shunt resistance value. If you want to read more about this H-bridge, how it works, what is the fundamental idea about this H-bridge, we can read this description thing. Similarly, for control PWM voltage, you can see there is a description option. We can go here and we can read about this control PWM voltage. Okay. Now, this is basically current sensor to measure the current value that is passing to the DC motor from this H-bridge. So it's connected in series, and the I port, that is basically the that will show us the sensing value. So it is showing it is connected with a scope, and the scope name is current to observe the current behavior. Then this is basically the DC motor, where the parameters are set like armature inductance is 0.01. Okay, so before that, this is a permanent magnet type of motor, and the model parameter is based on the rated load and speed. So as previously we talked, that at rated load the speed is 2500 and no load speed is 4000 RPM. Then the rated mechanical power is basically 10 watt, and rated DC supply voltage is 12 volt. And other mechanical parameter is set like rotor inertia, rotor damping, initial rotor speed is set to 0. And if we want to read more about this DC motor, we can go to this description option. Then this is basically the ideal rotational motion sensor to sense the RPM. So the sensed RPM value is connected. This W port is connected with a scope, where the scope named is as RPM, where we can observe the speed behavior over this simulation. Now here you can see, so the torque value, so this is the positive and negative terminal of the motor, and this is basically the rotor where the torque is transferring from C to R port. That's why R is connected with the ideal rotational motion sensor. So whenever we will connect any load, we need to connect it with R. So C is basically the reference. So we need to connect it with a rotational translational reference. If we just go here, we can see mechanical rotational reference. We need to connect it, this C port, with this. Then as we have to use a solver configuration block whenever we will design any Simscape model. So we need to connect it. That's why the solver configuration block is connected with this model. And also the negative terminal is connected with the electrical reference. You can see. Now, if I just go here, so already we have seen the parameters. If the value is, the simulation time is set it for 10 seconds. If I just run this model, it will take very small amount of time. So already it has run. So now if I just check the RPM or the motor speed characteristics, we can see the motor speed has increased from 0, and it almost settled near about 2000 rpm. So as we have discussed previously, that at 2.5 volt of voltage reference, this speed will be near about 2000 rpm. So that's why the 2000 rpm is set. So we can say this motor model is validated with our manufacturing dataset. Then this is the current scope. So if we want to monitor the current profile as well, we can see. So the current has increased from 0 to almost 1.7 amps. And then once the initial speed it touches, then it's settled down. So, and it comes near about 0 amps. Now, if we just change the reference voltage to validate the motor parameter for 5 volt, if we just change it and click enter and apply OK. Now, if I just run it, we can see now the RPM value will change and it will set around 4000 RPM. So you can see the RPM has increased. So let me just, yeah. So now you can see the RPM value has increased beyond 2000 RPM and it settled near about 4000 RPM. So we can say our motor data sheet is validated. Also, the current also will increase. So previously it was near about 1.7 amps. Now you can see the current has increased almost till 3.5 amps. Then it reduced and it settled down near about 0. As the initial speed it touches, it's set it to 0. So here there are two modes of simulation. The simulation mode. So previously we have set it this for average. If we just change this to PWM, so we can set to PWM, or also we need to change this for H-Bridge as well. We also need to change it to from average to PWM. So once we change it to PWM, it will just run for more, it will take more time to simulate. Otherwise, there will be some little bit changes in the characteristics, because it's a PWM mode to simulate this model. Now, if we just run this, we can see Now it is taking a bit more time to simulate. Once it is simulated, we can see. So the characteristics will not change, but it has touches 4000 RPM. We can see. So the characteristics is almost same, but it will take more time to simulate because the simulation mode is different, and based on the different mode, the mathematical operation that is going in background of this model, it is going to change. Here also we can see the current value is same, like it reaches almost till 3.5 amps, then it reduced and it settled near about 0 amps. What we can do, we can change the motor parameters for different motor datasets. Like we can increase the rated load from it's now set it to 10 watt only, but we can increase the motor load, we can increase the DC supply voltage, we can also connect a battery to it. Instead of this PWM reference voltage, we can connect a battery and we can simulate. So if I just change this, if I just take a battery from electrical source, so if I just connect the positive terminal with positive and negative terminal with negative, and if I just change the nominal voltage value, so it is 12 volt, let me change it to 240 volt. That's it. So I have set it to 240 volt. The battery charge capacity is infinite. We can change it to finite. Then I have to parameterize the capacity as well. So I am just keeping it infinite. Then inside the control PWM voltage, there is nothing to change, but in H-bridge, we have to change the output voltage amplitude because this is the voltage amplitude for our motor. So as we increase this battery voltage to 240 volt, so we must need to change the H-bridge this to, let's say our motor will be for 200 volt. So I'm setting to 200 volt, and then I will come to this DC motor. I will change this DC motor voltage to 200 volt, and I'm changing this rated torque to, let's say, 10 kilowatt. The other parameters, I'm just keeping it same. I don't have any other manufacturer parameter for any motor dataset, but I'm just changing only the rated load and the DC power supply voltage of this motor, and I'm just checking the characteristics, how it is going to behave. So once I have changed these things, I can run this model. So as the mode is PWM, it is taking some time. So it got run. And if I just open this RPM, now you can see the characteristics is not same. It increased till 6,000, then it more than 6,000, then it drops, then near about 4,000. At 4,000 RPM, it got settled. Similarly, the current also, here you can see for the first initial speed, the current has some pulses and it increased near about 47 amps, then it decreased, then again it increased, and almost it settled at some after some milliseconds. So then it set to 0 amps. Once the initial speed, it catches the initial speed, it settled to 0 amps. Similarly, once we want to develop any electric vehicle or hybrid electric vehicle model, what we can do, we can connect us speed reference to this, and we can connect a controller. Then we can connect this reference, speed reference with the controller, and we can give the input, or we can connect the port of the controller with the control PWM voltage, so that the behavior of the motor can be referred from that speed reference, and it behaves like the speed reference. So that's how we can simulate a DC motor that is controlled using PWM. So thank you. If you got any questions, please feel free to ask. Thank you.